Okay, last but not least, question second in the C part. Determine the time it takes the signal to arrive at the back of the cargo ship according to the spacecraft. Okay, so here again it asks us to see how the time is being observed from the spacecraft reference, and we can see that the event actually occur on the cargo ship, right? And now we're standing on the spacecraft to observe something happening here. So then the proper time should be in the cargo ship. And here I would have to say that we cannot apply the time dilation here, okay? Because basically the two events happen at two different positions. Why? Because the signal first emitted at the position F and then it arrived at the position B at the cargo ship. So that would be that at two different positions at two different time points. So that's why we cannot apply the time dilation here. And you can see why better at the end of this problem. So in order to solve this problem, we just have to follow the Lorentz transformation, okay? Whenever you came across the type of question related to like light signal emitted from one position and then arrive at another position, the best way to do it is just like using this way. This will be like the most easiest way, safest way, convenient way to solve for this kind of question, okay? So here, we go from the cargo ship and we transform everything to the spacecraft. So then we will need some gamma constant, right? The Lorentz factor. So Lorentz factor here has been calculated previously from question 2b here. You see? It's also like between the cargo ship and the spacecraft. So basically that's the same gamma. If you want to check how to calculate this one, just check the previous video, okay? Then here we go from the cargo ship. We can see that at the beginning, the signal is emitted from the F position. So for convenience, I will just assign that time point T at F to be 0, okay? And then it will take some time to arrive at B. That will be another event at B. So time at B will be the time it takes for the light to travel the whole length of the cargo ship that observed in the cargo ship. Then it should be the proper length itself divided by the speed of light, because that's how the signal travel, right? At the speed of light. It's a light signal. So this is the TB in the cargo ship reference frame. Now we transform everything from here to the spacecraft. So just using this equation, then we got TF prime will be gamma times what TF here, just plug in this one here. And now this is the V here. What is the V here? The V here should be the speed of the spacecraft relative to the cargo ship. So again, this one also have been calculated before. Here, you see. And this is like of the cargo ship relative to the spacecraft. So when we compare the spacecraft to the cargo ship, it will be the opposite direction, right? So the speed is also like the same, the magnitude is the same, but just in the opposite direction. And in here, we have to base on the cargo ship reference. So here, we take the F at the beginning, right? And then the B later. So we can assume that we got the positive direction is from F to B, okay? So then if this is from F to B, then we can see that this is the positive direction, okay? And then we also see that the spacecraft, it travels in this direction as well. So that's why the speed of the spacecraft relative to the cargo ship also positive, okay? It's positive in here. And then the same thing, apply the same equation for time TB. Then we got the TB prime here. So altogether, we can see that the time interval between these two variables, we got the later subtract by the initial. And then we got this one, TB, subtract by TF, that actually the interval in the cargo ship reference, right? Which is let me make it clearer, which is just the proper length divided by the speed of light, see? And then here, this one is a common factor, right? We factor it out and we got the xb minus xf. And then here we can see that xb is on the positive direction. That's why this one is like a positive value, and which is just the proper length. So then add everything in together, just like plug in the values. Then we can get this is like positive, positive, together positive. Then we have a negative here, okay? So that's why we can see there's a decrease in the time interval, which just means that the time observed from the spacecraft seems to be shorter, right? It's shorter than the time that measured in the cargo ship itself, in the rest frame here, in the prop. This is the proper time, and this is like the time observed from the spacecraft. And here we cannot apply the time dilation because it happened at 2 positions. So again here, if we apply the time dilation, if we mistakenly apply it, then you can see that the time observed from the spacecraft, we will say, okay, then it should be dilated from the proper time, then equals to gamma, time with the proper time. But then it should have, turns out to be like longer, right? Which is not the case in here, because it's just like 2 events happen at 2 positions. Okay, that's why again, time dilation cannot be applied in this case. Another way to look at this one is like when you assume the positive direction in this direction instead, then like from the back to the front, then you can also see that the velocity of the spacecraft in this case, okay, because the v is in this direction, then you can get that the velocity of the spacecraft relative to the cargo ship will be negative, okay? But then you also have like this is xb, this is xf, and they are increasing in this direction. It means that you will have xb minus xf to be negative, right? So if you got this term negative, that this term here negative, then you also got this one negative, then the whole thing here will be positive again. So then you also have a negative here. So it doesn't matter which positive direction you are assigned for the direction in the cargo ship, either towards the right or either towards the left. You always have this one should be a negative value, you know, when you plug in everything. But in the mark scheme, they provide you something like positive. That's why the mark scheme is wrong, unfortunately. And they also happen to find like the time is like greater, which is not correct, okay? So final conclusion, this should be the one. The time observed on the spacecraft is shorter compared to the proper time observed on a cargo ship. Okay? Let me know if you have any question. Thank you, and good luck in your practice these kind of questions related to special relativity. Okay?